So we're talking about an extremely powerful alliance between software and hardware.
It has the potential of a civilizational destruction. I think there should be some government oversight because it affects it's a danger to the public.
The era of AI is already underway, sparking concerns among scientists who advocate for its controlled development. However, there's a new player on the scene: quantum computers. But here's where it gets intriguing. The renowned physicist Michio Kaku has recently dropped a bombshell about the fusion of AI and quantum computers. Moreover, something strange is happening. What awaits us when these forces combine? Stay tuned as we dive into the beliefs of scientists and discover the insights from Michio Kaku himself. Before we delve into what the combination of AI and quantum computers can do, let's take a moment to understand the concept of quantum computing and its origins. To help grasp the idea of quantum computing, let's imagine you're in a massive library and you're on a quest to find a specific book. In traditional computing, you'd search for the book by meticulously examining each bookshelf and book one by one until you locate the desired one. This linear approach can be time-consuming and inefficient, especially if the book you seek is buried at the far end of the library. Now let's introduce quantum computing into the mix. In this scenario, each book in the library represents a different possibility or solution. Instead of searching linearly, a quantum computer can magically explore all the books at once. It can consider every possible path simultaneously and instantly pinpoint the exact location of the book you're looking for. Unlike traditional computers that rely on bits to store and process information, quantum computers have something way cooler called qubits. In regular computing, bits can only be in a 0 or 1 state. They're the building blocks of digital computing, used for calculations and storing data. But qubits in quantum computers are the real superheroes. They possess a remarkable quality called superposition, which allows them to exist in multiple states all at once. They can be both 0 and 1 simultaneously, juggling multiple possibilities effortlessly. This gives quantum computers mind-blowing computational abilities, as they can explore countless states and possibilities in parallel. And here's where things get even more mind-bending. Qubits can exhibit entanglement, a remarkable phenomenon where the state of one qubit becomes intrinsically linked to the state of another qubit, irrespective of their physical separation. This entanglement property bestows quantum computers with exponential computational capabilities, harnessing the power of interconnected qubits to solve complex problems. Now let's talk about how these quantum computers actually work. They go through a series of complex processes involving the preparation of qubits, tweaking their states, and measuring the final results. To set things in motion, the qubits are chilled to insanely low temperatures, almost absolute 0. This chilly environment helps minimize any interference from the surrounding world, ensuring that the qubits stay stable and focused on the task at hand. During computation, the quantum computer measures the qubits to extract information. But here's the thing about quantum computers. When you measure a qubit, it collapses into a single state, and all that amazing superposition and entanglement vanish in an instant. It's like a magician revealing their trick, and the magic disappears. To make the most out of the measurements before the collapse, quantum algorithms employ some advanced techniques. These techniques extract meaningful results while the superposition and entanglement are still intact, maximizing the power of quantum computation. So, what makes quantum computers so darn impressive? Well, it's because of the ability to solve certain problems at an exponential speed compared to regular computers. While regular computers plow through information one step at a time, quantum computers can tackle enormous amounts of data all at once, thanks to their superposition and entanglement mojo. Now, the origins of quantum computing can be traced back to the 1980s and 1990s. While the concept of quantum computing was first proposed by the brilliant mathematician and physicist Alan Turing, his work predates the development of quantum computing. He envisioned a future where machines could leverage the principles of quantum mechanics for incredibly efficient computation. Turing set the wheels in motion, inspiring scientists and researchers to explore the possibilities of quantum computing further. However, His idea remained mostly theoretical for several decades due to the challenges of practical implementation. It faced a bunch of challenges that made it difficult to bring to life. But in the 1970s, physicist Richard Feynman started making some serious progress that changed the game. Feynman's contributions were like a guiding light, pushing the field forward and laying the foundation for future breakthroughs. He proposed the revolutionary concept of quantum computation. Feynman envisioned a novel type of computer that could utilize the principles of quantum mechanics to solve complex problems beyond the capabilities of classical machines. His out-of-the-box thinking got people excited and kicked research into high gear, all intending to harness the power of quantum mechanics for computation. But you know what they say, real progress takes time. It wasn't until the 1990s that things started to heat up. In 1994, mathematician Peter Shor dropped a bombshell with his revolutionary algorithm. It showed that quantum computers could efficiently solve these mind-boggling integer factorization problems, and that was bad news for the security of public key encryption systems because it meant classical encryption algorithms were suddenly vulnerable. But it gets even more exciting. In 1995, the folks at the IBM Almaden Research Center took Shor's algorithm from theory to reality. They implemented it using nuclear magnetic resonance, NMR techniques. It was a major milestone, even though there were still limitations when it came to scalability. But hey, you gotta start somewhere, right? Around that same time, a group of brilliant physicists, Peter Shor, Andrew Steen, and Emmanuel Nil, made another mind-blowing discovery. They cracked the code on quantum error correction. It was like finding the secret sauce to protect quantum information from all those pesky errors that can mess things up. This was a huge step forward in building practical and reliable quantum computers, and the hits just kept on coming. In 1999, the team at IBM blew everyone away by successfully teleporting quantum states from one spot to another. And then in 2005, mathematician Daniel Simon introduced his algorithm that kicked classical algorithms to the curb for certain problems, speeding things up like crazy. Not to be outdone, in 2009, computer scientist Love Grover brought us his algorithm that made unstructured searches a breeze. When it comes to building quantum computers, research groups and companies have been making big strides in the experimental arena. Take, for instance, the collaboration between Google, NASA, and D-Wave Systems. Together, they developed the D-Wave 2 quantum computer, which hit the market in 2013 as one of the earliest commercially available quantum computers. What made it unique was its approach called adiabatic quantum computing, using superconducting qubits to tackle optimization problems. But just as things were picking up steam, a curveball came out of nowhere. External pressures from the government forced Google and NASA to put the brakes on their quantum computer development efforts. Talk about a setback. The D-Wave 2 quantum computer was all set and ready to go, but suddenly, its future became uncertain. However, in 2016, IBM came roaring onto the scene with something called the IBM Quantum Experience. This cloud-based platform allowed folks to tinker with a smaller-scale quantum computer featuring 5 superconducting qubits. The idea behind this initiative was to make quantum computing accessible to everyone and encourage collaboration within the quantum community. It opened up a world of possibilities for researchers and enthusiasts worldwide to dive into quantum algorithms and conduct experiments remotely. Fast forward to 2017, and we hit a significant milestone. Physicists at Yale University cracked the code on error-corrected qubits with their groundbreaking surface code architecture. This breakthrough paved the way for fault-tolerant quantum computing, where we can protect quantum information from pesky errors and decoherence. Then, in 2019, Google dropped a bombshell. Their research team, led by the brilliant John Martinez, unveiled their 53-qubit superconducting processor called Sycamore. And guess what? Sycamore outperformed classical computers. Sycamore accomplished a task in just 200 seconds that Google estimated would require a leading-edge supercomputer of approximately 10,000 years to complete. This marked a historic moment known as the Sycamore Supremacy Experiment. It was the first time a quantum computer had done something that even the most powerful classical supercomputers couldn't handle. Although the task wasn't immediately practical, it showcased the mind-boggling potential of quantum computers to achieve computational greatness beyond what classical systems can offer. Nowadays, companies like Google are working around the clock to bring practical and commercially viable quantum computers to life. At the same time, artificial intelligence has been making waves, with chatbots and AI tools already making their mark and more exciting developments on the horizon. However, the question remains, what will happen when AI and quantum computers merge? Recently, the renowned theoretical physicist Michio Kaku weighed in on the intriguing intersection between quantum computing and AI chatbots. AI chatbots are clever software programs that search the vast depths of the internet to gather information and provide responses to inquiries. These chatbots have become impressively proficient at supplying accurate answers to all sorts of questions, ranging from medical diagnoses based on symptoms to passing the bar exam. However, according to Michio Kaku, their ability to discern what is truly accurate or true is rather limited. Now let's bring in the big guns, quantum computers. So what happens when we combine quantum computing with AI chatbots? Michio Kaku foresees a powerful combination that could revolutionize various fields. But here's the main concern. As Michio Kaku points out, chatbots might unknowingly include false or inaccurate information in their responses. You see, these bots collect data from all over the place, and sometimes they inadvertently grab some made-up or nonsensical content. It's similar to when imaginative teenagers come up with wild science fiction stories. The problem is, chatbots can't tell fact from fiction, so they might unwittingly keep perpetuating falsehoods. That's not ideal when it comes to getting reliable information from them. This is where quantum computers come into play as a potential solution. These powerful machines have the ability to fact-check like nobody's business. They can sift through massive amounts of information and filter out the gibberish and inaccuracies. By tapping into the potential of quantum computing, we can determine the accuracy of statements and differentiate between what's partially true, false, or misleading. This is compared to having a super smart assistant that helps us navigate the sometimes murky waters of information overload. According to Michio Kaku, this integration of quantum computing will make AI and chatbots much more reliable. And the perks of quantum computers don't stop there. The possibilities are endless. But as we explore this new territory of quantum computing as a fact-checking tool, we must also consider some important questions. Who gets to control the information and decide what's real or true? Before we delve into the concerns and dangers posed by quantum computing, let's explore its numerous potential and see how quantum computers will revolutionize the world according to scientists. Scientists believe that quantum computers have the potential to make remarkable contributions across various fields, including the exciting realm of space exploration and the search for extraterrestrial life. These powerful machines can process massive amounts of data all at once, making it easier for scientists to analyze information from telescopes, space probes, and other instruments. Quantum algorithms like Grover's algorithm and the quantum Fourier transform can speed up complex data analysis tasks, leading to faster and more accurate results. Quantum computers can supercharge spacecraft navigation and trajectory optimization. Traditionally, calculating trajectories is a computationally intensive process that takes a lot of time. However, with quantum computers, scientists can solve complex optimization problems more efficiently, helping spacecraft reach their destinations using less fuel. They can determine optimal paths by considering factors like gravitational interactions and planetary alignments. Another key benefit of leveraging quantum computers is their ability to detect subtle patterns and anomalies in the data that could indicate the presence of extraterrestrial life. But that's not all they can do. Quantum computers also enable scientists to explore celestial bodies with greater precision, increasing the chances of discovering signs of extraterrestrial life. They are invaluable tools for simulating complex cosmic phenomena, like the extreme conditions within planets, exoplanet atmospheres, or cosmic ray interactions. By accurately simulating these phenomena, researchers gain insights into the habitability of exoplanets, the formation and evolution of galaxies, and the potential existence of extraterrestrial life. Quantum simulations offer opportunities to explore scenarios that are impossible to recreate in traditional laboratories, contributing to our understanding and detection of life beyond Earth. Secure communication is of utmost importance in space exploration, and quantum computers have the capability to transform it completely. By harnessing the principles of quantum mechanics, these computers can generate practically unbreakable encryption. Algorithms like quantum key distribution allow for the creation of complex encryption keys at an unprecedented rate, ensuring secure communication between spacecraft, satellites, and ground-based stations. This advancement in secure communication protects sensitive data and fosters collaborative efforts in the search for extraterrestrial life. Finally, when it comes to the search for extraterrestrial intelligence, quantum computing can greatly enhance the analysis of data from radio telescopes. By accelerating the search for artificial signals and distinguishing them from natural sources of interference, quantum computers can play a pivotal role in the quest to find signs of intelligent life beyond our planet. Quantum algorithms are capable of efficiently processing and analyzing large volumes of radio telescope data, identifying potential candidate signals for further investigation. But that's not all. Quantum computers can also revolutionize the field of cryptography and data security. Traditional cryptographic algorithms, which rely on the difficulty of certain math problems, could be at risk when faced with powerful quantum computers. However, the good news is that quantum computers themselves offer a solution to this predicament through the development of quantum-resistant encryption algorithms. One exciting area in cryptography is quantum cryptography, specifically quantum key distribution, QKD. It provides an ironclad method of encryption by leveraging the principles of quantum mechanics. Through QKD, two parties can securely exchange encryption keys, instantly detecting any attempts to intercept or eavesdrop on communication. This level of security guarantees the privacy and integrity of sensitive information like financial transactions, government communications, and classified data. Furthermore, quantum computers have the potential to enhance data security even further by enabling more advanced cryptographic techniques. For instance, lattice-based cryptography has shown promise in withstanding attacks from quantum computers. Quantum computers can efficiently process and analyze these lattice-based cryptographic algorithms, offering robust security measures against future threats. But wait, there's more. Quantum computers are set to revolutionize the field of drug discovery as well. Developing new drugs involves analyzing complex molecular structures, interactions, and properties. Here's where quantum computers shine. They can simulate the behavior of molecules at a quantum level, providing invaluable insights for drug discovery and optimization. With their immense computational power, quantum computers can handle the intricate calculations involved in modeling and simulating molecular interactions more efficiently than classical computers. By accurately simulating molecular behavior, researchers gain a deeper understanding of how potential drug compounds interact with biological targets. This insight allows for predicting drug effectiveness, toxicity, and potential side effects, enabling more targeted and efficient drug development. Quantum computers also excel in virtual screening, rapidly analyzing extensive databases of molecules to identify potential drug candidates. Quantum algorithms accelerate this process by efficiently searching and analyzing vast amounts of molecular data. This expedites the identification of molecules with desired properties, saving precious time and resources in the drug discovery pipeline. Moreover, quantum computers can assist in de novo drug design, creating new molecules computationally to match specific target properties. By leveraging quantum simulations, scientists can explore a broader chemical space and design molecules with improved efficacy and reduced side effects. This opens up exciting possibilities for the development of innovative and personalized medicines, potentially leading to groundbreaking advancements in the treatment of various diseases. Scientists also believe that quantum computers can revolutionize climate modeling and weather forecasting. You see, understanding climate patterns, extreme weather events, and long-term climate changes is super important for tackling climate challenges and planning for the future. Quantum computers have this amazing computational power that can make climate modeling much more accurate. They can crunch through huge amounts of data and solve complex equations to simulate interactions within the Earth's climate system. They take into account things like temperature, humidity, wind patterns, ocean currents, and more. By simulating all these factors at a quantum level, scientists can gain a deeper understanding of how our climate works and make more precise predictions. This improved climate modeling is a game changer when it comes to assessing the impacts of climate change and developing strategies to adapt and mitigate. With more accurate information, policymakers can make smarter decisions about how to allocate resources, plan infrastructure, and develop environmental policies. But it's not just climate modeling that benefits from quantum computing. Weather forecasting gets a big boost too. Quantum computers can process real-time meteorological data, which means we get more accurate and timely weather forecasts. This is especially important for predicting severe weather events like hurricanes and storms. With precise forecasts, we can better prepare for disasters, issue timely warnings, and allocate resources more effectively. And it doesn't stop there. Quantum computers also help with data assimilation and analysis. They can take data from satellites, weather stations, and other sources and incorporate it into climate models. This makes the models even more reliable and accurate, improving our understanding of the climate. But perhaps the most exciting part is that quantum computing enables the development of more sophisticated and high-resolution climate models. These models capture even the smallest details and regional variations, which means we get better predictions at the local level. This is a big deal for agriculture, energy, and water resource management industries that rely on accurate regional climate information. Even though quantum computer offers numerous potential and can revolutionize various fields, they also pose certain concerns and dangers that need to be addressed. One significant issue is the vulnerability of traditional cryptographic systems. These powerful machines have the ability to break the encryption algorithms we rely on, like RSA and ECC, resulting in malicious manipulations of the blockchain. Both RSA and ECC are commonly employed in digital communication, such as to secure online transactions, data encryption, and secure communication protocols. Another growing concern is the harvest now, decrypt later technique, where attackers steal encrypted data and retain it for future exploitation, counting on future advances in quantum computing to enable decryption. This poses a risk as even years later, the stolen encrypted content may still hold value for attackers. But it's not just about encryption. Quantum technology's immense problem-solving potential poses risks as nation-states could exploit it in warfare. If one military has quantum computing capabilities while its adversary does not, the information imbalance could leave the latter defenseless, outmatched, and vulnerable to strategic maneuvers at every stage. Meanwhile, another major concern with quantum computing is the widening digital divide in society. Due to its high cost, only the wealthy will have access to its powerful capabilities, potentially exacerbating existing inequalities. Those who cannot afford quantum computing services, whether individuals, companies, or governments, may be left at a disadvantage and fall behind. Quantum computers also pose risk when it comes to machine learning, especially with something called quantum machine learning. You see, deep neural networks, DNNs, are already known for being difficult to understand. But with quantum machine learning, it could become even more challenging to evaluate these DNNs and figure out how they make decisions based on data. Another thing to consider is the impact on human resources, HR. Many people talk about the amazing possibilities of quantum computing and how companies can benefit from it. But we must also think about the risks. The sudden boost in productivity and speed that quantum computing brings could overwhelm organizations. It's like having too many things to do at once and struggling to keep up. This could pose challenges in managing projects and multitasking effectively, and we want to avoid burning out our teams. Now, let's not forget about the supply chain for quantum computing. You might be surprised to know that it relies on something called helium-based cooling. This helps keep the particles in quantum systems stable. But here's the thing. Helium is not unlimited, and it can be quite expensive. So there are two risks here. First, companies need to make sure they can get enough helium to keep their quantum equipment running smoothly. Second, there's a risk that only a few operators will have access to enough helium, creating an imbalance and potential dependency. The widespread use of quantum computers could make our overall cybersecurity situation worse. As quantum computing continues to advance, it's going to impact many aspects of cybersecurity. Digital signatures, secure communication channels, and network infrastructure will all face new vulnerabilities. But not just that. The incredible power of quantum computers brings security vulnerabilities that we might not even be aware of yet. It will open up a new world for hackers and bad actors to exploit. With this much power, they could find weaknesses in technology systems that we didn't even know existed. It's a bit scary because the consequences could be unpredictable. But here's the thing. Quantum computing itself is pretty tricky. Quantum systems are super delicate and need precise conditions and extensive error correction mechanisms to stay stable and accurate. Even the tiniest disturbances or errors can mess up the reliability and integrity of the computations. Subscribe to Beyond Discovery and see you in the next episode.